All right, I'm going to go through the derivatives of log functions, section 3.6. Well, every time you're dealing with a log, the first thing that you always want to remember is that log base 10 of 100 is equal to 2. Why is that true? Because 10 squared is equal to 100. So that relationship between the two is pretty important. So that's the thing I ask you to call back all the time. So the question is, what's the derivative of log? So I'm going to get rid of that and write down y is equal to log base a of x. So how do I take the log of that? Well, I'm going to use implicit differentiation. I'm going to imply the derivative, but first I'm going to rearrange it. So I'm going to write a to the base, the exponent's y is equal to x. Base, exponent, answer. Now I'm going to take the derivative of this with respect to x. Now we never proved the derivative of b to the x is b to the x natural log of b, but I'm proving this one to you. So here we go. Um, the derivative of a to the y is a to the y natural log of the base. And then I have to have derivative of the inside. And the derivative of the inside is dy dx. There's an inside function there. Okay, the derivative of x to the just x with respect to x is, of course, 1. And then like we've done with implicit differentiation, we solve for dy dx, which means these two bad boys here are going to get divided over. So dy dx is equal to 1 over a to the y natural log of a. And a to the y, it's always nice to have your derivatives in terms of x instead of y, and we know that a to the y is equal to x because it's right there. So my final answer for the derivative of log is 1 over x natural log of a, the base. So to summarize this, basically what you do is you take whatever's here, you throw it on the bottom of the fraction, and you multiply it times the natural log of the base. And if you have an extra function there where I circled this, then of course you have to enact the chain rule. Okay, example 1. How am I going to take the log or the derivative of natural log? So I write down dy dx is equal to, now I have to remember what the base is on natural log. The base on natural log, of course, is e. So we do what the rule says. We take this thing here, right, whatever that is, throw it on the bottom of the fraction, and then we have natural log of the base. Natural log of the base would be natural log of e, but we know that the natural log of e is 1. So the derivative of natural log x is just 1 over x. So that's kind of like another rule that we just gained. All right, let's apply this with the chain rule. When log is not there, we know that it means log base 10, right? There's nothing there. It's log base 10. So what do? We write dy dx is equal to, take whatever's this there, throw it on the bottom of the fraction, the natural log of the base, so natural log of 10, but we have an inside function, so I have to tack on times the derivative of the inside. The derivative of this inside function, of course, is 3. These 3's cancel, and I'm left with 1 over x natural log of 10. So it's kind of like that 3 never existed, and it's kind of true. That 3 doesn't really exist with this, and I'll show you another way to look at this. So we could have written y equals log 3 plus log base 10 of x. So if we're taking, that's one of the properties of logs, right? When you have multiplication, you can change it to addition. So we do dy dx is equal to, well, that's just a number. So the derivative of a constant's 0, so that goes away. And so the derivative of um, the log 10 is 1 over x natural log of 10, which is what I had before. Example 2. Okay, we're going to do a chain rule, but this time I can't really, let me get a drink here. Chain rule, but it won't be like the last one. We have to really count on the sign there. We can't just throw the sign away like we kind of threw that 3 away. So the dy dx is equal to, the derivative of natural log is just take 1 over x. So whatever's right there, you throw it on the bottom of the fraction. And there's an inside function. So the inside function, derivative of the inside function would be cosine. Cosine over sine is cotangent. All right. Oh, I made kind of a cool lightning bolt thing, didn't I? The next topic is called logarithmic differentiation. This is how you can take the derivative. Let me make that a little bigger there. There we go. Here's how we can take the derivative of a function raised to the power of another function. That's where this is really useful. You cannot use the power rule with this. You can't multiply by x and subtract 1 from x. No, that doesn't work. So what we have here is we have a function and then it's raised to another functional power. And there's no way to do that unless you do logarithmic differentiation. Okay? So here's what logarithmic differentiation is. It really works awesome for this. And you can use it, you can actually do logarithmic differentiation on all functions, but here's where it particularly becomes useful because I don't know how to take the derivative of this any other way. So I'm going to do the golden rule of algebra. What I do to one side, I do to the other. I take the natural log of each side, and I get natural log of y is equal to natural log of x. And where does that exponent go? It flies to the front. So it's x natural log of x. So we're bringing that x down is what we're doing. And now we can go ahead and take the derivative of all of this with respect to x. And the first one we can't do, but I can take the derivative of natural log of y. The derivative of natural log of y is 1 over y. But I have an inside function, so I tack in dy dx equals, now I do the what rule? Aha, the product rule. So I'm going to multiply this out. Derivative of the first with respect to x, so there's no implying the derivative here. It's all explicit differentiation. So the derivative of the first is 1 times the second plus the derivative of the second is 1 over x times the first, which is x. So the derivative of the first is 1 times the second. Derivative of the second is 1 over x times the first. Now we do a little simplifying here. Let me extend my page, bring this back up to right there. So we get 1 over y dy dx, dy dx, not dx dx, dy dx is equal to natural log x plus 1. Now I need to solve for dy dx. I'm going to multiply the y over. So dy dx is equal to y times natural log x plus 1. And y can have, like I said before, it's nice when you can have your derivatives be in terms of x. So I know what y is. Y is x to the x power. So dy dx is x to the x power, natural log x plus 1. And that's the logarithmic differentiation. Logarithmic differentiation, like I said, you can do it on any function. You can do logarithmic differentiation to find the derivative. You could do this, y equals x squared. You could do logarithmic differentiation to find that the derivative of that is 2x. It'd be a little bit overkill, but you could actually do it that way. Take the natural log of each side. In fact, try it on your own. But where it works the best is when you have this function raised to another function. All right, so that's this section. Problems that you're doing are right here. They'll be on the Google Classroom. And good luck with this.